says calculate the wavelength, typo, so that's how you can tell I made it, this problem. Calculate the wavelength in nanometers of electromagnetic radiation with a frequency. Okay, so now we're on a new topic and the second part of the lecture outline for this week. It says, and so now we are calculating the wavelength. We are talking about electromagnetic radiation. And from the lecture outline, electromagnetic radiation includes visible light, and visible light, it includes other things too, but let me talk about visible light for a minute. Visible light has wavelengths. Well, different people use slightly different numbers here, but I typically use 400 nanometers to 700 nanometers, and some people also use 750 nanometers. And if you do the rainbow of colors, and the rainbow of colors go Roy G. Biv, where R is red and V is violet, with the other colors in between. So red is the 700 nanometers, and violet is the 400 nanometers. And what you have to know about this, although it doesn't enter into this problem, is that red light has longer wavelength. That much I think is apparent because the wavelength is the number here in nanometers. But it also has shorter frequency, as we'll see, and lower energy. Whereas violet has a shorter wavelength higher frequency, and higher energy. And another way to remember this too, by the way, for me, is other types of electromagnetic radiation include ultraviolet, and ultraviolet would be beyond or below the ultraviolet, and ultraviolet causes sunburn on skin. And sunburn is caused because the ultraviolet is even higher energy. And on the other side, at longer wavelengths than 700 nanometers, is infrared. And infrared is also known as heat. And if you've ever seen, they have night vision goggles that can see heat. So they're actually seeing the infrared radiation that people's bodies give off, which is pretty cool. But it's also lower energy even than red. And cell phone signals are way out here too, at even lower energy. Now let me actually solve the problem that we're here for. It says calculate the wavelength with a frequency of 6.22 times 10 to the 14th seconds to the minus 1. The equation for this looks like this. C, which is the speed of light, which is 3.00 times 10 to the 8th meters per second. is equal to wavelength times frequency. We've been given our frequency in seconds to the minus 1, which is the same thing as 1 over seconds. So let's go ahead and plug into this equation now. So 3.00 times 10 to the 8th meters per second equals wavelength, and sorry I didn't mention this before, this is the lowercase Greek letter lambda, times frequency, which is this V, funny V with a hat on the back of it, 6.22 times 10 to the plus 14 seconds to the minus 1. Then I can bring this over to the other side. I get that my wavelength is going to be 3.00 times 10 to the 8th divided by 6.22 exponent 14. And I get 4.82 times 10 to the minus 7th. And as far as a unit analysis here, you can see that per second is, so seconds is in the denominator over here. 1 over seconds is means that seconds is in the denominator here. So my seconds cancel out, and I'm left with units of meters here. However, I've been asked to post my answer in terms of nanometers. And to turn it into nanometers, we have to realize that 1 nanometer is 1 times 10 to the minus 9 meters. And so I will take my 4.82 exponent 7 minus, and I'll divide it by 1 exponent 9 minus, and get 482 nanometers. There we go. And that 482 number is the number that you will put in for this. Any questions about that? Okay.
Take picture.
Go ahead.
Yeah, I want to take picture. Thank you.
Sure.
Thank you.
All right. Oop. I guess I can stop recording.